Today we are going to go to the lecture 4 of the 4G subject, and we're going to start looking at the interface structure a little bit more deeply. So we're going to have a look at the structure of the LTE radio frame. What are the protocols that are used in the LTE physical layer? And I'm going to look at a little bit of MIMO as well. So we have 4 parts to cover today, and hopefully we'll have enough time to go through all of it. Let's start off with the radio frame structure. We started looking at these concepts a little bit last week. We talked about the idea of a radio block. Today, in the FDD mode, we have a separation of downlink and uplink. And we also saw that the radio frames that are transmitted on the uplink are not on the same carrier as the downlink. And this is referred to as type 1. So in type 1, both in type 1 as well as in type 2, the radio frame length is 10 milliseconds. And on the uplink direction, we have 10 subframes, each of a duration 1 millisecond. And 1 millisecond corresponds to 2 resource blocks, or a PRB, as we referred to last week. So within a radio frame, we have 10 subframes. So just now I told you that the radio frame has a duration of 10 milliseconds. So if you have 10 subframes, the duration of each one of these subframes is 1 millisecond, which we also refer to as TTI last. Okay, and within each one of these subframes, we have 2 slots, each of duration 0.5 milliseconds. Okay, so just to recap, a radio frame duration 10 milliseconds is made up of 10 subframes, and in each subframe we have 2 slots, and the number of symbols that you transmit in each time slot depends on the type of cyclic prefix that you use. In the case that you use a normal cyclic prefix, you transmit 7 OFDMA symbols, and between each OFDMA symbol there is a guard interval of 4.7 microseconds. In the case of the extended cyclic prefix, we use a time interval of 16.7 microseconds, and we did some calculations in the tutorial questions towards the end of last week. And we said that in this case we would have 6 OFDMA symbols. So we are transmitting 1 less OFDMA symbol in the case that we use a larger cyclic prefix. Now what happens in the case of TDD? The previous slide was more related to FDD. In the case of TDD, again we have the radio frame is still 10 milliseconds as in the case of FDD, but what we normally do is we divide this frame, this 10 millisecond frames, into 2 half frames of 5 milliseconds each. Okay, and within a half frame we have essentially 5 subframes, but one of the subframes is used for signaling purposes. So it's used to transmit the downlink pilot, and there's a guard period followed by transmission of the uplink pilot signal. Remember, the downlink pilot and the uplink pilots are used to estimate the channel quality, which is a very important aspect of OFDMA based systems. So essentially what we do is, out of these 5 subframes that form a half frame, only 4 are effectively used. One is essentially reserved for sending control information. I wouldn't say control information, more information that is needed more for measurements and so forth. Now there are different options. Now sometimes you may want to have equal amount of uplink and downlink transmission, and sometimes you may not. You may want to give, especially in the case of TDD, you may want to give more resources for downlink transmission compared to uplink transmission. Okay, so because of that reason, in the TDD mode, we have the option of dividing the subframes into uplink, which are given the symbol U, and downlink, which are given the symbol D. Okay, and we also have these special subframes that are essentially there to tell you that there is a changeover from one format to another. So this is one of the advantages of the LTE TDD mode, is that it's possible to dynamically change the uplink downlink balance based on load conditions. So you can change this on a dynamic basis. It's not something that needs to be fixed in the system. Okay, so even from one frame to the next frame, so every 10 milliseconds, basically you can change the uplink downlink balance based on channel traffic conditions. So for example, if there's a lot of downlink traffic to be transmitted and there's very little uplink traffic, then you might decide to choose format number 5, okay, up down configuration number 5, because number 5 has probably got the highest number of downlink subframes compared to the others. There are, how many in this one? There is 8 downlink subframes and 1 uplink subframe. So again, it's one of the things that in a lot of the specification, they also try to make the LTE sort of backward compatible with the UMTS system. Okay, now those of you who've done some UMTS will know that we had a 10 millisecond frame in UMTS. So again, you can see that the frame length that's been adapted in LTE is also 10 milliseconds. So it's the same frame length that they're using. So again, you can, and also some of the things that we saw last week, they try to make the sampling frequency multiples of 3.84 megabits per second, so that it's backward compatible with the 3G network. Okay, that's a very important criteria, because we sort of discussed this concept last week, but I'll just recap it. The basic building block of OFDMA is called a resource block. Okay, a resource block is essentially 12 subcarriers and making up 180 kilohertz, because we know subcarrier spacing is 15 kilohertz. Similarly, we have that's on the frequency dimension. On the time dimension, we saw when we're using normal cyclic prefix, we had 7 OFDMA symbols. Okay, so 7 OFDMA symbols multiplied by 180 kilohertz is referred to as a resource block. Okay, so that's the basic. Just as we talk about a time slot in GSM, the basic building block in LTE is a resource block. Now, a resource block is each one of these. If you think of these as little bricks, each one of these bricks is referred to as a resource element, and a resource element has a bandwidth of 15 kilohertz and a duration. Do you remember the duration from what we did last week? The duration of a symbol in the time domain was 66.66 microseconds. Okay, and then you add the cyclic prefix to it. Okay, so that is a resource element, and within a resource element, a symbol is transmitted, and the number of bits that are essentially put into a resource element depends on the type of modulation scheme we use. For example, if you use QPSK, we are transmitting 2 bits. Effectively, we are transmitting 2 bits within that resource element. If we are using 64 QAM, we'll be transmitting 6 bits inside this resource block. Okay, again, that depends on the modulation scheme that is being used. So, but essentially, it's one OFDMA symbol. So, just a couple of points. A resource block is comprised of many resource elements, and each resource element can either carry 2 bits if you're using QPSK, 4 bits if you're using 16 QAM, or 6 bits if you're using 64 QAM. And how many resource elements are there in a resource block? Well, if you're using normal cyclic prefix, we have 12 into 7, which is 84 resource elements. If you're using the extended cyclic prefix, which are used to cover the larger cells, you will have 12 into 6, which is 72 resource elements. Okay, so another way to pictorially describe a resource block is shown in this slide here. I hope you have that slide. Yes, you should have it. So here again, you can see that a resource block is this block that's been has a dark border to it, and it's made up of. Okay, now the number of resource blocks you have in a particular for a particular operator depends on the kind of bandwidth they have. Okay, so an operator that has only 5 megahertz of bandwidth will only have, if they're operating in FDD mode, for example, they will have 25 resource blocks for the uplink and 25 resource block on the downlink. So that at most you could only have. Okay, now normally we don't deal with a resource block. We deal with something called physical resource block. That means we allocate 2 resource blocks for every user. Okay, and a physical resource block is essentially made up of 2 resource blocks. So in the case of a normal cyclic prefix, we'll have 14 OFDMA symbols. Okay, that's 7 OFDMA symbol in each slot across 12 subcarriers. And this again will have a duration of 1 millisecond. The next concept that we're going to look at is something called a resource element group. Okay, so we've talked about a resource element. We've talked about the concept of a symbol. So I think these are key terms that you should know. You should know the difference between these terms. You should know the difference between a symbol, a subcarrier, a resource element, a resource block, a physical resource block, and a resource element group. Okay, so a couple of terms. They look very similar, but they mean quite different things. So it's very important that you know the difference between them. Now, when we do signaling, it's very wasteful if we give an entire resource block to a user of any kind of signaling. So what we do is, for signaling, we take a portion of a resource block, and that is referred to as a resource element group. So in this case, a resource element group could be the first symbol So, and 6 subcarrier positions. Okay, that could form a resource element group, and you could do all your control channel information being sent on this one symbol. It's just like those of you who've studied GSM, you know that in the case of GSM, we take the first time slot, and we, on this first time slot, which is referred to as common control channel, we put in a number of logical channels which carry a different signaling information. Okay, and that's the same idea. Try and pack as much signaling information as possible within this resource element group. The next thing I'm going to look at is the protocol stack. So in the protocol stack, what are the important protocols? Well, this diagram here shows the various protocols that are used for communication across the air interface. Remember, the air interface is always the most difficult transmission link over which you've got to get your information. So you've got on the air interface, if you work from the bottommost layer upwards, the bottommost layer is a physical layer. Okay, the physical layer is where you package information into these OFDMA symbols and subcarriers and so forth. The layer above it is referred to as the MAC layer, media access control layer. And the media access control layer performs a number of functions, but probably one of the most important function it has to perform is scheduling. It's got to schedule how packets will be transmitted on subcarriers. Okay, because essentially we've got packets that are coming in from higher layers of the protocol stack, and these have to be eventually transmitted into these physical resource blocks. So how do we take these various packets and package them? Which physical resource block do we use? So the MAC layer is quite complex in the eNodeB. So in fact, when we've gone from the previous technologies, like when we've gone from GSM to UMTS to HSDPA to LTE, the MAC layer has got more and more complex. And now, because everything is in the form of packets, the complexity of the MAC layer is really it's probably one of the most complex MAC layers in all of the mobile technologies. Above that, we have the RLC, the radio link control layer. Okay, the radio link control layer is about how do we have a reliable radio link between the UE and eNodeB. So it has a set of procedures that are there to make sure that information is transmitted reliably between the two endpoints. PDCP, okay, this is a term that has come all the way from the GPRS era. Okay, so and then above that we have the PDCP layer. PDCP layer is the packet data convergence protocol layer. Okay, this is, as I said, is the layer that compresses the header. For example, if you're doing an FTP session, okay, you can see that when you look at a FTP session, if you look at the IP packets that are being transmitted, there's very little difference from one IP header to the next IP header. Maybe only a few fields will change. So the question is, why do you want to continuously transmit that IP header, which is just wasting information? So you compress the header, you only leave the most useful information in it, and you transmit it. Okay, that's one of the important functions of the PDCP layer. Again, very similar. Even in we had the same thing in a 3G network as well. We had to form header. We do header compression there as well. Okay, so let's move on. So, as in any communication, you will have the same protocol layer at the eNodeB as well as at the UE. Okay, and these entities, these PDCP layer here is only communicating with the PDCP layer there. Okay, And in order for it to communicate with its peer PDCP entity, it passes data to RLC, and RLC might add a header and then pass it down to MAC layer. MAC layer might decide how to schedule it, pass it to the physical layer, then it goes over OFDMA to the UE, for example, and the reverse process is done until the PDCP. So the PDCP layer at the UE is communicating with the PDCP layer at the E node B. Similarly, the RLC layer at E node B is communicating with the RLC layer at the UE, and so forth. Now, there are different normally in most mobile communication and in telecommunication in general, we have two types of data. We have something called the user plane, and we have something called the control plane. User plane is where all the user data is transmitted. Okay, for example, if you're chatting with somebody on VoIP, the transmission of all those VoIP packets will be user plane. If you're downloading a file, if you're listening to some audio, if you're doing audio streaming on your 4G phone, all of that is user plane information. But in order for data to be transmitted, a lot of control information has to be continuously transmitted between the two ends, okay, so that this communication link can continue to be there, and that's why we have this control plane. So again, very important that you understand the difference between the user plane and control plane if you're hearing it for the first time. Now, we have something called non-access stratum, and we talked about this in the second lecture, NAS, and essentially all the signaling that takes place between the UE and core network is referred to as non-access stratum, okay, and things like messages that need to be sent between UE and the MME, okay, initially in the process of setting up a connection, there's a lot of messages that may have to be sent between UE and MME, and so forth. So all this signaling that takes place between the user equipment and the core network is referred to as non-access stratum. Now, below that, we have something called RRC. Now, again, for those of you who've been in 3G, this might you've probably come across a similar term before, RRC, and RRC is the radio resource connection. Again, I'm telling you, with most mobile communication, you get a lot of acronyms, and I don't expect you to remember them straight away. But over a period of time, as you read this material again and again, you will sort of have a better idea of what they are. So the RRC is a protocol that's only used in the control plane. So it's a protocol that is used to set up a bearer. Remember, before any communication gets started, we have the concept of a bearer that needs to be set up between the UE and the E node B, and between the E node B and the rest of the network. So the setting up of this bearer is an important function of the RRC. Now, so this concept of radio bearer is something that's applicable between the PDCP and between one PDCP layer and another PDCP layer. Again, as I said before, the PDCP layer is again inherited from the 3G, okay, and again we use the radio bearer concept in 3G as well. Now, the link between the next layer below the PDCP is the RLC layer, the radio link control layer, and between one radio link control layer and another radio link control layer, we have something called a logical channel. Okay, and again, this is also something that we saw both in 3G as well as in 2G. And between the MAC layer entities, the channel that is created between them is referred to as a transport channel. Again, that is also inherited from the 3G space. Okay, so a little bit of terminology. We've come across these two terms, PDU and SDU. Okay, PDU refers to protocol data unit, and SDU refers to service data unit. Okay, so every layer in a protocol stack, what it receives from the layer above it is referred to as a SDU, a service data unit. And when it receives that, it adds its own header. Okay, and that becomes the PDU that this layer has produced for the corresponding or the peer entity at the other end of the communication link. Okay, so it's very important that you understand the difference between the terms PDU and SDU. Okay, two protocols at the same layer or two peer protocols exchange PDUs, whereas a layer above and a layer below exchange SDUs. Okay. Same ones and zeros, but they have we use different terminologies to distinguish between them. Okay, we move on to each one of the protocol layers and just discuss them briefly again. So the radio resource connection protocol, as I said, that only works on the control plane, and there is a RRC protocol is implemented in the E node B as well as in the UE. Now the main difference between 4G and 3G is that in 3G, especially in wideband CDMA, the RRC was implemented at the RNC, whereas now it's being implemented at the E node B. So the RRC is the highest protocol in the control plane on the radio side, and what does it do? It allows the RRC layer in the E node B to exchange signaling messages with the RRC layer in the UE. Apart from that, it also allows other signaling messages from the higher layers, such as the non-access strata messages, which we just talked about, to be exchanged between the UE and the packet core network through the RRC layer. Okay, so here it just forwards a message. It doesn't process anything. It just forwards a message to the appropriate network element. So what are the functions? It performs a whole lot of functions. Okay, all the RRC functions are described. So we have establishment, maintenance, and release of an RRC connection between UE and UTRAN, which is referred to as a radio bearer. Mobility management functions. So as a UE moves around, you want to be able to track where it's located, sometime at cell level, sometime at a high level. And we've already discussed that it directs messages, the NAS messages, to and from the UE. It also has to perform broadcast of system information, and there's a lot of information about the cellular network that needs to be broadcast. So the UEs can make decision based on this broadcast. Examples would be things like cell ID would be one type of information that is broadcast by every cell. Another function that the RRC layer has to do is paging. That means if you have an incoming call, you've got to be able to locate the subscriber to see which particular cell the subscriber is located in, and the RRC function gets involved in that. And it also, the UEs are also constantly reporting measurements. So all of those functions is also done through the RRC layer. Now, remember, all of these functions that are described here, these are all purely control plane information. Okay, it's got nothing to do with user traffic. But these procedures are necessary so that a connection can be established, data can be transferred, and so forth. Okay, so RRC functions all related to the control plane. Now, in the RRC connected states, there are two possible states that a UE can be in. A UE can be either in something that is referred to as the RRC connected state. So, in the connected state, you established a bearer, and the network can transmit and receive data from the network. And when you are in the RRC connected state, the location of the UE is known at cell level. Okay. The next possible state, you can only be in one of these two states. Either you are connected to the network or you're idle. That means you don't have a connection to the network. So when you're in the RRC idle state, you're not connected, there's no radio link, there's no radio bearer. Okay, and the network knows that the UE is present. And if there is an incoming call, it knows how to reach it. It knows how to invoke paging procedures to be able to locate the cell the particular UE is located at. So basically, when you're in the connected state and you don't have any traffic to transmit, after a certain timer condition take place, you get moved on to the RRC idle state. Okay, so you only stay in. We want to try and keep every user in the idle state if they're not transmitting data. Obviously, if they have data to transmit, we have to keep them in the connected state. But as soon as you realize that user equipment has not been transmitting data for a certain period of time, we quickly switch it down to RRC idle state, because when you're in the RRC idle state, you are using up less resources to maintain that particular UE. Next, we move on to the PDCP layer, Packet Data Convergence Protocol layer. Again, we've got a very similar layer in the context of 3G. And the main function of PDCP is IP header compression and decompression. So if you compress the IP headers on one end of that communication link, at the other end of the communication link, you've got to decompress before you send it on to the higher layer. And the procedure that is used for IP header compression and decompression refers to as ROHC, robust header compression. Apart from header compression, there's also ciphering. Whenever we transmit anything across the interface, we cipher data. So both the user plane data as well as the control plane data is ciphered before transmission. And sometimes in the process of handovers, the upper layer PDUs could arrive in a different order to the order in which they were transmitted from the transmitter. So in that case, you need to rearrange the PDUs in the correct order before you send it up to the higher layer. And that's what is meant by in-sequence delivery of packets. So both on the control plane as well as on the user plane, we make sure there is ciphering of information that's transmitted across the interface. Again, a little bit more details about the PDCP layer. Okay, an example being, we know that the IP header has about 20 octets of information, which contains a whole lot of things, such as for example, a 32-bit IP address. This is in terms of for IP version 4. Okay, we may have a 32-bit IP destination address, 32-bit IP source address, then a whole lot of fields like TTL, time to live, fragmentation offset, and all of those information is transmitted on every IP packet, because that is specified by IP, so that's something that cannot be changed. Okay, but what we can do is we can, as it goes across the air interface, we can get rid of unnecessary information. So for example, in the case of an FTP transfer, a lot of the packets will have very similar IP headers. So the question is, why do you want to continuously transmit the same information? And so we have this compression method by which we remove all duplicate information. So what we can do is we can reduce from the PDCP header itself will only have 1 or 2 octet, but it can reduce the IP header considerably. The next layer is RLC. Okay, again, these modes, the RLC can operate in 3 possible modes. The same, very similar to what we did when we had a look at 3G. So we can have transparent mode, unacknowledged mode, and acknowledged mode. Okay, so what is the difference? Well, before we do that, let's just look at the basic functions of RLC. One of the things RLC has to do is the SDUs that it receives from the high layer could be of very different sizes. So if you have very large size SDUs coming in, we may have to segment it into smaller size. And the other thing we have to do is remember the RLC layer. Above the RLC layer we have the radio bearer concept, and below the RLC we have a logical channel. So we have to map signals from the radio bearer level to the logical channel level. So I talked about these 3 modes. What is the difference? Well, in transparent mode, it's a mode which we use for real-time service, and here we don't do any retransmission. Okay, most of the time when we deal with real-time traffic, such as voice or real-time video, we don't do retransmission. We discard. If information is in error, we discard it, because we know that the source, the sink of the information, which could be the human ear or the human eye, it's able to cope with certain amount of error. Okay, so transparent mode is used for that purpose. In unacknowledged mode, this is where again we don't retransmit here, and again this one is used for signaling purposes. And the third mode is the acknowledged mode, and this is where we have retransmission taking place. So when will that occur? If you have errors in the communication, there is a mechanism by which the RLC layer will retransmit any information that has been received in error. Okay. The MAC layer deals with finding out if there is an error, but once it finds out it's an error, it will be the RLC layer that will retransmit the layer, and this is used for non-real-time services. The next layer is the MAC layer, and as I mentioned earlier on, the MAC layer is a layer that performs all of the scheduling functions. Okay, and so above the MAC layer we have the logical channel, and below the MAC layer we have the transport channel. So the MAC layer has to perform mapping between the logical channel and the transport channel. It also has to perform scheduling, by which it allocates resources for all the packets that are waiting for downlink transmission or uplink transmission. So the MAC layer in the E node B performs all the scheduling decisions for both uplink transmission as well as downlink transmission. So this is the point that I have just mentioned, that it's the E node B, it's the scheduler in the E node B that determines dynamically on a 1 millisecond by 1 millisecond basis which UEs are supposed to receive data on the downlink channel and on the uplink channel. And as I mentioned before, the resource block or the physical PRB is the basic unit that is allocated to users. Now the other thing that the MAC layer also performs is that it based on some feedback that it receives, it changes the modulation and coding scheme, and this is referred to as link adaptation, and we sort of briefly mentioned it before. So both in the uplink direction as well as in the downlink direction, there are measurements being taken about the channel quality, and that channel quality measurement is used to adapt the link, as referred to as link adaptation. Okay, this is what we mean, a little a diagram to explain that concept. So the UE that we have here will take these downlink channel quality measurements, and it will send that up to the scheduler, which is in the MAC layer, and the scheduler will then take the data that's sitting in the buffer for downlink transmission, and it will decide what modulation and coding scheme has to be used to transmit that particular data on the assigned resource block. And it chooses the modulation and coding scheme based on a number of things. So the scheduler will use, okay, how much data is sitting in the UE buffer. Okay, does the UE need one resource, one PRB, or does it need two PRBs? Okay, and what type of data is sitting in the buffer? Is it real-time data or non-real-time data? Okay, remember, if it's real-time data, we have to try and get that data through the link, transmission link, as quickly as possible. The other thing that you need to consider is what sort of radio resource is available. Okay, and what is the condition. So you have to take into account all these four factors when the scheduler decides how it's going to assign the PRBs to various users. And after it decides which PRB is being allocated to which user, it also has to decide what modulation and coding scheme should be used on. Now the same thing happens in uplink as well. In the uplink direction, again the UE is taking, the scheduler is, in this case, is taking measurements, and the UE, when it's got data to transmit, it will send a request to transmit message, and the scheduler will receive it. And remember, in uplink transmission, the data is sitting in the UE buffer. So here the scheduler will get similar requests to transmit from all the UEs that are being served by the E node B, and it also knows, it's also measuring the uplink channel quality measurement. Okay, and based on the uplink channel quality measurements and information such as the amount of data that's sitting in the buffer, it will decide which resource block should be allocated to which UE, and also the modulation and coding scheme that's going to be used on every resource block. Okay, that's a quick introduction to the various protocols that we have. Okay, we move on to the radio channels. Okay, previously I talked to you about this idea of a radio bearer, a logical channel, transport channel, and a physical channel. Okay, so these are these terms here. A radio bearer is essentially set up between two PDCP layers. A logical channel exists between the RLCs layers, a transport channel exists between two peer MAC entities, and a physical channel is the bottommost layer that exists at physical layer. So, and a lot of these concepts are very similar to what we had in the 3G scenario. Okay, physical channel, transport channel, and logical channel. So, it's always very difficult to explain some of these concepts, but a logical channel is about answering what is being transported. Okay, in the GSM network, we used to say a physical channel is a time slot, but within the time slot, we can have many logical channels. Okay, the same sort of idea happens here as well. These three types of channels existed from the 3G era. Now, if we move on, now what sort of logical channels do we remember? Remember, we have something called broadcast channel, cell ID, tracking area ID. You know, anything that needs to be sent to all the users in the network is sent on the broadcast channel. Okay, so what do we know about broadcast channel? What else do we know about broadcast channel? It's downlink, exactly. It's purely a downlink communication. Okay, there's no broadcast on the uplink. Okay, and the next type of channel that we use is for paging. Okay, so paging again is used for when you want to know the location. When the network wants to know the location at cell level of a UE, we have paging messages being sent on the paging channel. Again, it's a downlink channel. You never page on the uplink. Okay. The third type of channel that we have is the common control channel, CCH. Okay. For those of you who've done GSM or 3G, you know that these terms are all familiar from. So common control channels are channels in which you send control information, but these channels are common to all the UEs. Okay, so it's not a dedicated control channel. So in control channels, there are essentially two types of control channels. You can either have common control channels, which are used by all the UEs, and the whole idea of using a common control channel is to get a dedicated control channel. Okay, and once you get a dedicated control channel, that will be only dedicated for that particular UE for control messages. So what would be an example of a common control channel? Do you remember? Sorry? Random access channel, RACH. You all remember RICH, RACH. Any other channels? Okay, that will be a downlink. That is specifying which it's giving you the resources. Okay, so we have common control channels and we have dedicated control channels. Okay. Then there's also because of the possibility of multicast taking place, there's also a logical channel that has been specified for multicast. So multicast is a downlink channel used for transmitting MBMS control information. Okay, now this part of the lecture is going to be very, very boring because it's essentially reading material, but I'll try to go through this as quickly as possible to try and keep you awake. So, yeah.
Is MBMS control information different from that we are transmitting on some other channels? Is there difference between
It's whenever you have a multicast, when you have a multicasting session, you have multicasting data as well as multicasting control information.
That is different from?
It's different from the dedicated.
No, multicasting is for a certain group that is being connected to that for the specified group, but do the information is different?
What do you mean information?
The bearer information or whatever?
This is, we're just talking at logical channel level. Okay, so in order, when we have a multicast session, any multicast session when we set up, you need to send data, which is for all the users, but you also need to send control information. So that's what the MTCH, the previous one, MCCH is used for. It's essentially a control channel. Remember, all these are sort of control information. They're not traffic information.
So what is the example? What kind of control information does a multicast group can need from? What kind of? Can you give some examples of what kind of information they might need?
Okay, there might be a possibility where somebody might want to join a multicast. Okay, or somebody might have to be deleted from a multicast. Okay, or sometimes a multicast user could ask for a larger size bearer. Okay, so those are all possibilities. Okay. Okay, in the traffic channels, you have dedicated traffic channels and multicast traffic. So we introduce one more term, and in the transport channel, we have something called a transport block. Okay? So remember this word. Remember, I told you 6 things that you have to know the difference between. What were they? Resource element, symbol, subcarrier, resource block, PRB, resource element group, and transport block. 7 things. Transport blocks. So a transport block is transmitted every 1 millisecond. Okay, every TTI. So a transport block, format of the transport block depends on a number of factors. It depends on what sort of modulation and coding schemes you have, and also the number of PRBs that were allocated and so forth. Okay, that's so in the transport channels, we have 3 important channels, and I'm just going to state what they are. I'm not going to go into the details of each. So we have the broadcast. So remember, we've gone now in transport channels. We have BCH, broadcast channel, downlink shared channels, which is used for the transmission of data, and we have the paging channel, PCH, and the multicast channel as well. So that's where all the multicast information is transmitted. Okay, so if, probably this diagram is a better diagram. We talked about 7. We talked about 7 types of logical channels, and we talked about transport channels. So each one of these logical channels is mapped into the appropriate transport channel. So obviously the PCCH will go into the PCH. The broadcast channel will either go into one of these states depending on what type of broadcast it is. The command control channel will go on the downlink channel, and so forth. Again, I'm not expecting you to know. Okay, now we move on to the physical layer, the physical channel, which is probably a little bit more interesting. So we have this concept of a transport block, and this transport block comes into the physical layer. So the first thing that happens to the transport block is we add a CRC, cyclic redundancy check, which is used for error control purposes. At the receiver, you take the transport TB again and you recompute the CRC corresponding to the TB. And if the 2 CRCs, the CRC that is computed at the receiver is different from the CRC that came along with the data, then you know that some corruption has taken place to the transport block. So this is where the retransmission mechanism comes in, and it requires, it asks the transmitter to retransmit. And again, that's only done for the acknowledge mode. It's not done in the other 2 modes that we talked about. Now, once you add the CRC, the next thing that you do is you you perform the coding function, interleaving function, and after that it goes to the HARQ process, and then you have data modulations where you modulate your data, and once your data is modulated, it needs to be put into a resource block. Okay, so for example, you may have a strings of 1 coming along, and if in the case that you're going to use 16 QAM for this resource block, you'll take 4 bits at a time and package them into represent that by a symbol in each resource element. Okay, and this will be done in the context of a in the physical channel. Okay, so there's also there's 2 terms, physical channel and physical signal. Okay, when we talk about physical channel, we are talking about information that's coming from the high layer, whereas when we talk about physical signal, this is information, this is a signal that does not carry information from the upper layer, but it's used for synchronization and measurement. So there's basically the difference is there's sometimes you need to take measurements and you need signals to synchronize a mobile. We'll talk about the synchronization process in the next lecture, but you need certain signals that need to be transmitted for that. And whereas when we talk about these information here, these are information that are predominantly either in the user plane or control plane that are needed for communication to be set up. Okay, so remember the difference between these 2 terms as well. Okay, and then again in the physical channel, you can have the important ones probably are the PRACH, which is a random access channel. Okay, this is something that should be familiar to you. This is the channel on which you send a RACH message to be able to set up and it's an uplink message. And once you send the RACH, you get allocated a control channel, and once you have a control channel, you establish your connection, and then you get allocated a data channel. So it's always the 3-phase procedure where initially you send a RACH, then you get allocated a control channel. Once you have the control channel, you do whatever signaling is necessary before you start getting allocated a data channel. And the data channel has to be set up both in the uplink as well as downlink. Okay, again a diagram showing how the different logical channels are mapped into the transport channels and into the physical channel. The next thing is we're just going to look at uplink data transmission. Okay, remember in the uplink direction, each user UE might be transmitting on different resource blocks, and these resource blocks could be on different parts of the spectrum so that they don't interfere with each other. Whereas in the downlink, you could be allocated your the resource blocks that you're allocated could be anywhere in the spectrum because it's downlink information, and from one TTI to the next TTI, the resource blocks that you get allocated will be different. So for example, in this case, this UE, these might have been these ones were allocated for UE2, okay, and these resource blocks were allocated for UE1, but in the previous TTI, it might have been other way around. So you can be allocated from one TTI to another TTI. You can be allocated a completely different set of resource blocks, okay, and that's the reason we are able to do that in OFDMA based networks because of the feedback that UEs are continuously sending back to the eNode B saying, these are the resource blocks on which I'm getting good channel conditions, and use that information to packet scheduling uses that information to schedule resources appropriately. Okay.